Welcome everybody. Last talk of the afternoon is Mina Karzand from University of California, Davis. She will be talking about representation cost of linear neural networks, analysis and design.
Thank you. So this is joint work with Zhen Dai, who's a PhD student at the Applied Math department at UChicago, and Nati Cerebro at TTIC. So the classic problem of supervised learning is that given a training set with n samples, you're going to learn a function in some function class such that f of x is a good predictor of the labels y. And we're going to focus on parameterized mapping such that these functions are from inputs and are described or determined by these p-dimensional parameters w, and f of x and w is the learner's prediction about the label. And we try to have it as close as possible to y. So the learning algorithm would be learning the parameters w given the training set based on the training set. And usually we use some form of optimization algorithm to do that. Most of the talk will be about neural networks in which these parameterized functions are associated with some architecture in which there are activation functions, and the input goes through layers, and in each layer there is a weight matrix that mixes things, and then there's an activation function. Typical choices of activation function are ReLU, sigmoid, identity functions, and in this talk we're going to focus on linear neural networks, so the activation functions are just going to be identity functions. So basically your function is just going to be multiplication of various matrices times the input. So typically in applications, neural networks operate in overparameterized regimes, which you could define differently. You could say that the number of parameters is larger than the number of samples that you have, or the capacity of the class of functions is much larger than what you need to describe the data or to fit the data. But now the question is, one of the questions is that given a sample set and an overparameterized class of functions, there could exist many functions in this class of functions that fit the data perfectly. And now the question is, which one generalizes well? Which one should we pick? This is a classic example in which you have 11 points. And then if you fit it using a linear function, then you cannot fit all the data. But if you use a polynomial of degree 10, then you fit it perfectly, but you probably overfit, so it doesn't generalize. Now, if you try to use a polynomial of degree 17, for example, there are many curves that fit the data perfectly, and you have a choice to, which one you're going to pick. In the past few years, there has been a few interesting observations, empirical observations. We've seen these many times so far, that in practice, when we increase the capacity of our function class, obviously the training error goes down, and eventually actually it reaches zero. So we have zero training loss, but the test error goes down and actually doesn't come up, or comes up and then again goes down. So this is the surprising part, that even though we have zero training error and we're interpolating, still the model generalizes. Similar curves have been seen before. I'm going to talk a little bit about double descent curve paper by Misha, that similar curves have been seen in other setups, that again, the training error reaches zero and the test error keeps on going down. And this promoted this idea of double descent curve, that the training loss is going to go down as the capacity of your class of functions increases, but the test error goes down and up. This is the U curve, which is classic machine learning underfitting, overfitting. But then after this interpolation threshold, we're in the overparameterized regime. In this regime, there are many functions that can interpolate the data. And with the proper choice of this interpolating function, maybe we can have risk going down in the overparameterized regime. So in a nutshell, it seems that the capacity of the function class does not reflect the generalization property. We should look into something else. And it seems that in this overparameterized regime, a regularity or smoothness of the functions are somehow measured by some form of function norm, and that's what determines the generalization properties. We're going to talk a lot about this notion of regularity or smoothness. In addition, it seems that by increasing the capacity of H, we're just looking at the larger class of functions, and we are able to find interpolating functions that have actually smaller norms, so they're actually smoother. So we're hoping that that's the by finding smoother functions, the generalization is going to get better. So again, this is one of the classic examples in which you have 10 data points, and if you use a 2-layer ReLU network with 40 hidden nodes, you can interpolate, but the curve that you get is not necessarily smooth. But with 4,000 hidden nodes, you get a much smoother function. And other experiments show that actually there's this notion of norm of the weights, that actually after you enter the interpolative regime, the norm of the weights go down at the same time as the generalization improves. So it seems that the keyword is minimum norm interpolation, that you're not just interpolating, you're trying to find this smoothest interpolator possible corresponding to some notion of minimum norm. So there's a relationship between minimum norm, smoothness, regularization, and we all hope that all of these will help us with the generalization. So just to put it in some notation, what we're trying to find is looking at the class of functions F, we're gonna look at all the functions G such that they interpolate, so they fit the data perfectly. But among all these functions that interpolate, we're gonna find the argmin of some cost over G. So there is this notion of cost of representation cost of G, and we're going to find, the output of the learning algorithm is going to be the minimum representation cost of G, such that G interpolates. Now we're going to talk a little bit about what should be this loss function or the cost function, there has been a lot of work recently about that in the field. I'm not going to review all of them. But the basic idea is that there is this marriage between optimization algorithms and the learning or the generalization. But basically, our choice of optimization algorithms are helping us go toward finding these interpolators that have minimum L2 norm of the parameter. So in the case of parameterized mappings, especially neural networks, we're seeing all these examples in which both theoretically and in empirical results, the L2 norm of the weights is penalized, and that's what we're seeing as the output of the algorithm. Motivated by all this conversation about the implicit regularization, by the way, this is one of the results that I talked about, that gradient descent on homogeneous models implicitly regularize the L2 norm of the parameters. And even if we don't think about the implicit regularization, there's this idea of explicit regularization, which in practice we do weight decay a lot of the times, that we try to minimize the training loss, but also we try to use the weight decay. And motivated by both of these, we're gonna look into this minimum norm interpolators, such that if my function is a parametric function. So I just want to emphasize on the notation here a little bit. This f of x and w was the parametric function from input x and parameters w to output y. So this capital F of W now is a function from X to Y. And the output of the learning algorithm is trying to find these weights such that I want to find W's such that F of W on Xi is going to be Yi for all I. But at the same time, I want to minimize the L2 norm of W's. So this is the representation of what the algorithm seems to be doing in the parameter space. But we can write the same thing in the function space, that now my output, the learned model F, is going to be argmin of this cost function over G, such that G's are in these functions in the function class, and they interpolate well. But now I have to define this representation cost of G. This is the formulation that we wanted to get into. And the representation cost of a specific function G is actually the minimum norm of minimum L2 squared norm of W's, such that f of W is equal to G. Again, I want to emphasize that f of W and G are both functions from X to Y. So there are two minimizations here. Among all the functions in F that interpolate, I'm going to look at all the functions that in F that interpolate. And for each G, I'm going to look into all weights or all the parameters that represent G. Remember that my parametric representation might be redundant. There might be many, many different realizations of the weights that give me the same function. So I'm going to look at all these weights and look at which one gives me the minimum L2 squared norm. And that would be the representation cost of G. And now the output of the learning algorithm is going to be the G that interpolates and also has the minimum representation cost. And even if we don't have exactly like minimum norm interpolation and we have some form of regularization, we can have the similar formulation that maybe we want to have the minimize the empirical loss of some learner with parameters W and penalize L2 norm of W. This is exactly the same as the same minimization, but in the function space. And now that I want to find a function G in the calligraphic F or the image of this parameterization F, such that the minimum cost representation of G is minimized. Or sorry, this is it's used as a penalty. So the goal of this talk is understanding the relationship between these formulations, understanding how minimizing the or penalizing L2 norm of parameters affects the penalization or regularization of in the function space. And in practice, and in particular, I want to emphasize that we don't actually really care about the minimum cost representation or the representation cost. What we care about is the representation cost up to some equivalence, where the equivalence is defined by, you can define it as the ordering that it induces over the functions in your function class. So if two representation costs induce the same ordering over all functions in my function class, they're equivalent because the output of this algorithm is going to be the same for these two representations. Or one is the monotonic function of the other. So these are two examples in which, if you have, for example, two networks, for one of them representation cost of G is equal to representation cost of G in the other one to the power of 2 for all G's, then these two the output of these two networks will always be the same according to this formulation. And the other one is that we say that a neural network induces L1 norm as its complexity measure if the representation cost is monotonic to L1. So all I want to say is that representation cost is only important up to this equivalence of monotonic functions. And that's what we call the induced complexity measure in the function space. That this is the measure of complexity. When we say that in the overparameterized regime, we want to find the least complex function that interpolates. It means that we want to find, this is the measure of complexity that we're using basically. And that's the thing that determines generalization properties of the networks, because that's the thing that determines what is the output of the algorithm. Now, what is the talk about? The talk is about understanding the relationship between induced complexity measure and the architectures of the deep network or the neural network. In particular, we have two questions in mind. One is analysis, one is its design. That given an architecture or specific properties of the architecture, what can we say about the induced complexity measure? And in particular, if we assume that the L2 norm of the parameters is penalized, what is the penalization in the function space? In the design, we look at the other way, that if I, as a user, know that for some reason my data prefers some form of regularization in function space, how can I change my network or design my network in a way that's the induced complexity measure, that these are the regularization. For example, if I want to construct a linear network such that it penalizes LP norm of linear coefficients, how should I do that? What kind of network does that? Throughout the talk, we're going to talk about, we're going to focus on linear neural networks, and in particular, so the input-output relationship is just going to be like this. So the network just operates as a product of some matrices. So first, let's talk about the analysis part. And the first network that we look into is the linear fully connected neural network, in which we have these D matrices. I'm assuming that I'm not losing rank between input and output. The number of hidden nodes is large enough. So the relationship between input and output is like that. And I'm assuming, again, that there's no weight sharing. These matrices are independent of each other. And given a specific linear function, G is equal to beta x, where M is the dimensionality of the output and N is the dimensionality of the input, the minimum cost representation of this beta is going to be this formulation, that I'm going to look at all W's such that product of W's is equal to beta. And the cost is a summation of Frobenius norm of W's. That's the L2 norm of the parameter vector W if you just stack them on top of each other. This has been seen before in a previous paper, that the representation cost of this network is has this formulation, D times summation of sigma I to the power of 2 over D, where sigma I is the singular values of matrix beta. The proof is kind of very intuitive, so I suggest you think about it for a minute. If I want to have this formulation, there's no reason that WIs shouldn't align. If they don't align, I'm losing a spectral power on the way between input to output. So as soon as they align, they can commute. So there's symmetry, so there should be some kind of equivalence. They should be equal to each other. Obviously, there's a lot of details that I'm skipping here because the sizes can be different, and then I have to think about the rank of beta, and that's what matters, and so on. But basically, we're going to see that the singular value decomposition of W's are going to be very similar to singular value decomposition. Sorry, the singular values of W's are going to have a relationship with the singular values of beta, but the singular vectors just need to align. So the induced complexity measure is going to be 2 over D Chatten quasi-norm of beta. And in particular, when we're looking at the single output case where M is equal to 1, the induced complexity measure is just the L2 norm of the vector beta. So again, yeah. No, the singular value is the norm of the matrix, the norm of the vector.
So it's not the 2 over no,
beta here is a matrix, here is a vector. So that's the result about fully connected neural network. As I said, most of this was known before, but this is like the most heuristic thing. That's why I put it here. The next example is diagonal neural networks. This is the figure. So in words, basically, you have these vectors, D-1 vectors that determine the weights from layer 1 to D-1, and then the last layer is a fully connected layer. So the representation cost is again defined as the minimum over summation of Frobenius norms. But now I want this property to hold. The last layer times this diagonal matrices should be equal to beta. Again, if you think about it, the proof, it's not that difficult. Again, these diagonal matrices can commute, so that helps a lot. But now the representation cost of a given matrix beta is going to have this form, and the induced complexity measure is this group norm of L 2 over D and D norm. I don't know if I've ever mentioned, but D is the depth of the network. And in the case of single output where m is equal to 1, this is the induced complexity measure is now going to be L2 over D norm of beta, where beta is a vector. Next, we're going to talk about convolutional neural networks. In the case of full width convolutional neural networks, where the operation between input to output is just a bunch of convolutions at d-1 layers, and again the last layer is fully connected. Again, this result was seen before. You want to minimize the L2 norm of W's subject to reconstruction. The trick is very simple. It's using discrete Fourier transform on everything, basically. As soon as you use discrete Fourier transform on the circulant matrices, they become diagonal. And you can just do something very similar to what you did for the diagonal matrix networks, but this time it's on Fourier domain. So the representation cost is going to look like this. And the induced complexity measure, again, is a group norm of L2 over D and 2 on the Fourier representation of beta. And in the case of single output, it's just going to be L2 over D of beta hat. But the problem is that in practice, we don't usually use full width convolutional neural networks. We use restricted width convolutional neural networks in which just some edges are removed. And this corresponds to having these vectors that have only Q non-zero elements. And then you construct these circular matrices from them and just apply them. But now finding the representation cost of restricted width convolutional neural networks is very surprisingly very difficult. I spent a lot of time thinking about it, and it's not clear even if there's a closed form solution. We have a bunch of results that we're going to talk about it. Parallel to our work, some other people, including Surya, Mina, and Ilyas, have a paper that get very similar lemmas to our paper, but they use semi-definite programming techniques. The results, as I said, are kind of partial and just making some observations. The first result is that in a two-layer network, if the filter width is equal to 1 and we have single output, the representation cost is going to be L2 norm of Fourier domain. If the Q is equal to N, which means that you have full width, the representation cost is going to be, the induced complexity is going to be L1 norm of Fourier domain. And in practice, essentially, for any general Q, the induced complexity is going to be between L1 and L2. So it's going to interpolate these two things, but it's not clear how exactly that happens. Make some additional observations that, clearly the representation cost should be decreasing in Q. And the reason is that as you increase Q, you're basically adding edges. So the representation cost cannot go up, but it is not strictly decreasing. We have a counterexample for that shows that there are cases in which this is not strictly decreasing. In other results, we show that if Q divides N, again, N is the input dimension and Q is the filter width, then the representation cost for Q with filter width Q is going to be upper and lower bounded by the representation cost of the CNN with one filter tap within a factor of 1 over square root Q. And the other result says that the representation cost of multi-channel CNN does not depend on N, the number of channels, the number of outputs. We showed it for Q equal to 1 and N, and these people showed it for general Q. The other kind of analysis results that we have is related to residual neural networks, in which basically you start from a homogeneous neural network and you skip some layers. So in the case of linear non-homogeneous neural network, we can show it by starting from a homogeneous network N and then constructing these compact networks N1 to Nk, such that each of them are basically selecting a bunch of layers. And then the ResNet is going to be summation of these compact networks. Again, finding the closed form solution of representation cost of resonance is very difficult, but we've showed that if we think about the depth of these component networks, such that the first one is the most shallow one and the last one is the deepest one, then for the first equation, this one says that if your input is extremely small, if the linear coefficients are very small, then the representation cost looks like the representation cost of the most shallow one. And if the linear coefficients are very large, then the representation cost of ResNet is very similar to the representation cost of the deepest network. There is a simple and kind of interesting example which looks at this network, which is just a summation of a fully connected one-layer network plus a diagonal two-layer network. And then we showed that the representation cost of that is just going to have this form, where R of beta I is a unique positive root of some equation. So this is a very implicit form of showing the representation cost. But then we could show it for different values of beta I. And as you see, for a small value of beta I, it looks like L2 norm. And for large value of beta I, it looks like L1 norm. And for anything in between, it basically interpolates. So as you see, this is the L1 norm is the representation cost of the diagonal network with one layer, which is the deeper component. And L2 norm is the representation cost of fully connected one layer network, which is the most shallow one. So now thinking about the design part, given some common regularization functions in the function space, we want to construct architectures that induce these penalties in the function space. We're going to focus again on linear networks, but almost all results that we have in this part is on single output networks. So the first and simplest and kind of cleanest result is on LP norm, that if we care about inducing LP norm as the regularization in the function space, then first of all, this is only possible using linear homogeneous networks if 2/p is a natural number. And also we saw that diagonal network of depth 2/p actually induces this. So the interesting part here is that if 2/p is not a natural number, no linear homogeneous network can induce this LP as the regularization or as a penalization, representation cost in the function domain. So this is related to this notion of mixing depths that I find interesting. So mixing depth is kind of simple. So for any subset of nodes S, you can find the first layer in which you find a node that's connected to all these nodes in S. And that's the mixing depth of S. Let's look at another example just to show. So for these nodes in red, the mixing depth of these two nodes is actually 1, 2, 3, the layer 3. This is the first time that you see a node that connects these nodes from input to output, and all of them are connected to that node. But the mixing depth of the first 3 nodes is just going to be here, right? That's the first time that they're mixed together. So this has a lot of the interpretation about how the network is treating different dimensions, and actually this result about LP norm is just saying that the representation cost is LP if and only if for all subsets of n, the mixing depth is 2/p. So that the diagonal network satisfies this property clearly. The first time that you have the mixing of all the subsets is the last layer, which is 2/p. But there are networks that are not exactly diagonal. There is some redundancy in the network, and still they satisfy this property. So this is the exact formulation of what we need in a network to show that LP is the regularization. The next regularizer that we care about is the LP group norm. So for given partitioning of numbers from 1 to n, LPQ is defined as that. So just, LQ over each graph, each group, and then LP over, between the groups. And then we have results that show that, first of all, this can be the induced complexity measure only if 2 over P and 2 over Q are natural numbers again. And if P is less than Q, we show the architectures that have this as the regularization, as a complexity measure. But if P is greater than Q, we only construct the architecture for this very specific case that 2 over P is equal to 2 over Q minus 1. And for other cases, we actually don't know what architecture shows that. So when P is less than Q, and we care about, as I said, LPQ, the architecture that has this induced complexity measure is the one in which it's diagonal in the first D minus 1 elements, but it's diagonal only for each group. So the nodes in blue are in one group and the nodes in red are in another group. And then after the 2 layers from the input, you mix different groups with each other. So again, note that this is the case that P is less than Q, and you care about the LQ norm inside the group, and D1 is 2 over Q. So that's how you're mixing, the groups with each other and so on. So again, this has a very nice representation in terms of the mixing depths. For the other case that P is greater than Q, the representation is slightly different. For D1 minus 1, so D1 is 2 over P. For the first D1 layers, you just have diagonal. But the next layer, you have one node corresponding to each element of Cartesian product of the groups. So you have one node that's connected to one element from each group, and so on. That's how you're mixing different groups with each other. And as I said, for the general case of P greater than Q, the architecture is not known. The last example that I'm going to talk about is the K-support norms, which are defined as follows. This is like a summation of L2 norms between different subsets of 1 to n, such that support of each of these elements is an I. I is the subsets of n. And the summation of all of them construct beta. And we showed that K-support norms are actually achievable using linear neural networks. And for that, we need a 2-layer network where each node is connected to one of the groups, one of the subsets of size. So each node corresponds to one subset of size k of the n input dimensions. So this is the brief summary of the results that I mentioned. But we had some observations about the limitations of homogeneous neural networks, not only linear but homogeneous neural networks. For example, we showed that if we looked at LP quasi-norm with overlapping between the groups, not the groups do not partition 1 to n, but they have overlap. Or if you look at elastic nets, which is linear combination of L1 and L2 norms as the regularizations in the function space, no homogeneous neural network can achieve these as the induced complexity measure. But we showed some non-homogeneous parameterizations that actually can achieve these things. So there are certain cases, it is also, the general case is interesting, that what are the regularizations that can be achieved with the homogeneous parameterizations and what are the ones that cannot. So overall, some of the future work that I find interesting and important is the most pressing one might be the the representation cost of convolutional neural networks with finite filter width. The design component with multiple output is actually not known. There are not that many results that we know about that. Again, nonlinear activation function And general description of properties of architectures that help us achieve these induced complexities is also not known. And using this framework in the pipeline, understanding the connection between this representation cost to the generalization properties and so on is also important.
Questions? So a natural question is, this is assuming that you really minimize this cost, right?
Yes.
But in practice, you
Yes.
run some algorithm,
Yes.
etc. Do you have any idea of that? How that changes the effective regularization?
That's an important question. Yeah.
Any other questions? I guess everybody's tired. So thanks again, Mina. That's it, folks.